Okay, we're set. Okay, so that is the first integrated circuit that was made in 1966. That is a logic gate that used only, I think, 6 transistors, intercoupled logic, the digital circuit, digital integrated circuit. So that looks quite crude, right? So that was the first integrated circuit. And that is from today's modern time, that integrated circuit, some expanded view. Not today's, 1971, it's a Pentium Intel 4004. It has only 1,000 transistors, speed about 1 megahertz. So that is how it looked like. Still, you can see the small components here. And that is in 2001. It has 42 million transistors. So 1,000 transistors to 42 million. So in 30 years time. So you cannot see anything here, right? Just it's so different. It's like a city, right? A big. If you took the picture from very high above and high altitude, so it looks like a city, and different roads and houses, buildings. Right? So it has 1.2 billion transistors, Intel Core Quad, in 2011. So, now, why analog? Why we're starting analog? Because now today's everybody is, and the focus towards the digital technology, and we're also trying to make it a digital Bangladesh. So everybody loves the digital, right? Digital technology. Now, why we're starting analog? So in reality, though, we think that everything is becoming digitized, right? And so ultimately analog will disappear from our life, but that is not the case, because what is written here, digital circuits has increased the importance of analog circuit, as most digital systems need analog circuits to interface to the real world, because our real world is analog, right? Real world is analog. In our voice signals, right, these video signals, those are analog signals, and then those analog signals are converted into digital signals, then those are processed, right? So but to interface with the real world, we need analog signal. Before you convert those into digital, you need to process the analog signals. So there comes the role of the analog circuits. So you cannot do without the analog circuits. It will be always there, no matter how much digitized you make your systems. So this is our digital system called digital world, right? And that is interfacing with the outside analog world. And what we can have in our outside analog world, we can have sensors, actuators, right? We can have microphones, audio devices, right? We can have images, displays, storage media. We have electromagnetic devices. We have phone lines. So those are phone lines today are also, and they send signals in digital signal form. So these are we can have in our analog world is different kinds of analog devices, and that will process the analog signals and then communicate with this digital system. Our nature is analog world, and we need an analog to digital interface, right, between these two. So, but we have sensor transistors, we have interfacing circuits, and then we have digital processing, then goes to the digital system, right? So here we have amplifiers in between filters, analog to digital converter, digital to analog converters. So these are the most prominent of the analog devices that are widely used in any digital systems. So transmitter and receiver circuits building block, right? So that is where we need analog circuits very much. Right? You receive the signal, analog signal, you do the signal conditioning, convert it into digital form. And when you want to transmit the signal, you convert the digital signal into analog signal, right? Do some conditioning of the signal and then transmit. This is this transmitter receiver circuit, the chip that shows the board. On the one single chip, you have both the analog circuits and also the digital circuits. Right? So most of the analog digital chip will also have some analog integrated circuit on the same chip. The microcontrollers, we call it a digital circuit, right? Digital IC chip. But it also have analog component. Every microcontroller will have some analog to digital or digital to analog converter, and those are analog circuits. So what are the course objectives? We'll try to provide students with a foundation in the analysis and design of most commonly used analog integrated circuits in both bipolar and CMOS technologies. So first we try to get an idea about the analog integrated circuits and how we design the different components and how to analyze those different circuit building blocks of the analog integrated circuits. And we will provide you a state-of-the-art review of the principles, concepts, techniques that are needed to successfully design of analog integrated circuits. So far you have learned about the discrete electronic circuits, right, in device 1 and device 2. Now we are going into another area, right, where we learn about the analog integrated circuit, and the design techniques of analog integrated circuits is very different from the design techniques of discrete electronic circuits. There are new concepts, there are new techniques that are used to design the analog integrated circuits, because analog integrated circuits, they have to be fabricated in one single chip, they have to be much compact, and they are supposed to consume less power. So these things we have to keep in mind while designing these analog integrated circuits. So that has led to development of the new techniques and new concepts to design of analog integrated circuits. Okay, so we'll apply the first. Okay, before going into the details in this course, we try to mostly understand the inside circuitry of the op-amp. How the inside circuitry is constructed, how it is designed. It is an integrated circuit. An integrated circuit will have different building blocks, circuit building blocks. We try to learn those different building blocks. And first we discuss what led to the development of the op-amp. What motivated the development of the op-amp? Almost a century back, in the Bell Lab, they are trying to transmit the signals over a very long distance through the wired connections. It's 100 of kilometers from one city to another city. And they faced a problem of the signal getting very weak, and it was getting buried under the noise when they are trying to transmit over a long distance. So they are trying to develop amplifiers that will have stable gain so that they can boost the gain every few kilometers and also suppress the noise. And they want who are in need of an amplifier that will provide them a stable gain and reduce the noise. So in the quest of the search for an amplifier with reduced gain, with a stable gain and less noisy, scientist Harold Black, he came up with this concept of feedback. We discussed the theory of feedback in our device 2 course, the theory of feedback, how feedback is applied to the amplifier, and how it stabilizes the gain of the amplifier. So this is just review here and how it works and how it is applied to the amplifier and how it led to the construction of the op-amp. The theory of the feedback, we have a basic amplifier and we have a feedback network. And the feedback network, it collects the signal from the output of the amplifier and produces a feedback signal, and that is at the input side mixed with the source signal. Now the difference between these two is supplied to the input of the basic amplifier, Xi. So the difference between our actual signal and the feedback signal is applied to the input of the basic amplifier, and that is amplifier. And that is how the signal will flow. It is called this signal flow diagram of a negative feedback amplifier. The signal negative because it is subtracted, feedback signal is subtracted from the source signal. And the overall gain of this amplifier is given by this AF is A divided by 1 plus A beta. AF is the gain, and then the output signal divided by source signal, and that gain expression is something like this. Now, in this expression, if the product A beta is much larger than 1, then this we can approximate to A beta. 1 plus A beta, we can approximate to A beta. So the gain AF now becomes 1 over beta. So the overall gain of this amplifier reduces to 1 over beta. And this gain expression, it is independent of the gain A of the basic amplifier. The basic amplifier is not very stable. It can vary depending on many factors, especially the temperature greatly affects the gain of the amplifier. So if you can make the overall gain independent of the gain of the basic amplifier, you can achieve very stable gain for your amplifier. Now in this case, the gain of the overall gain of this amplifier, feedback amplifier, depends only on the feedback factor. Feedback factor depends on the how the feedback network is constructed. Usually it is made with the resistive elements, and resistive elements, the change in resistance with temperature is very minimal. So you get a pretty stable gain with the feedback network. Right? So that is the main concept, or that is how it developed and that is applied. So almost a century back. Now to make a successful feedback amplifier, one of the very important part, you have the basic amplifier, you can easily construct the feedback network with resistors. That is not a problem at all. The main critical part, crucial part is here at the input side, where you need to mix the two signals and get a difference between these two signals, and that has to be very accurate. And the performance of the overall amplifier will depend critically on the performance of how accurately these two signals are mixed at the input side. So that was the critical part of this feedback amplifier. Okay, I don't have anything here. So after the development of the integrated circuit, right, when they can put many circuit components on single device and make it smaller, compact. So scientists start looking for an amplifier that will integrate all these different parts in one single device. So they are trying to integrate this basic amplifier and also this what we can call it summer or something together in one single chip. So that was the main motivation, so that you can have it, because the feedback network you can easily construct by connecting the resistors, so that's not a problem. So main part was, the critical part was this summation at the input side and the basic amplifier. So scientists were looking to develop an integrated circuit that will combine these two in one single device, and then you just have this feedback network connected, right? And then you get the out. And that is how the op-amp was developed, right? And in op-amp, you see that op-amp has two input terminals, and the op-amp takes the difference between those two and amplify the difference. So these two are the input terminals of the op-amp, right? One is the signal source, another will come from the feedback network, and then inside the op-amp you have some circuit that will take the difference, and then the difference it will supply to the basic amplifier, and that will go to the output, and that is together they will make our op-amp. Guys, any question? So this block right here, this block together will be your op-amp. Right? This is the feedback network, right? Where you will have basically what you have feedback. You have the two resistors, R2 and R1. Right? So in that case, now R2, R1, so that may forms the feedback network, and your gain is 1 over beta, right? So 1 over beta, beta is the feedback network. That is the XF by the, you can see here that is your feedback factor XF by X naught. XF is the voltage at this point, X naught is the voltage at this point. So if you apply the your what you call the voltage divider rule, so you can easily write that XF by X naught is R1 divided by R1 plus R2. Okay. So that is applying the voltage division rule. So you get this feedback factor beta. Now, if you take the inverse of that, you get 1 plus R2 by R1. So that is the gain that we know that our gain of the amplifier, the op-amp amplifier in non-inverting configuration. Non-inverting configuration, we apply the voltage here at the positive input terminal, and the R2, the feedback resistor, connects the output to the inverting input terminal, and R1 here is grounded. So, and that is how we get a pretty stable gain for the amplifier, because we have just two resistors, ratio of the two resistors, and also there will be minimal change in the R2 and R1 with temperature, but even that will be cancelled out because you are taking the ratio, and both changes by the same amount. Any question, guys? Okay, now, so that was the basic concept, and that was the main motivation that led to the development of the op-amp, which will combine the component of the feedback amplifier, that is some kind of circuitry that will take the difference between the two input signals. So op-amp has, you see that it has two input terminals. One is the positive, we call non-inverting terminal, and it's the negative, which is called the inverting input terminal, and op-amp takes the difference between these two input terminals, right? So what we have in the op-amp, so we have two input terminals. One is positive and the another is negative. Right? So at the input side, we have this just using a symbol, right? And it's kind of let's call it. We'll take the difference between the two signals. I call difference amplifier. So similar, it has two input terminals. At the input side, we will have a difference amplifier that will. Oh my gosh. So we have as creating a problem. And input at the input side, we'll have a circuitry that will take the difference between the two signals, and then that will be fed to an amplifier, right? To an amplifier. Yes, it has a gain A. And that will amplify the signal, right? So this is our, we can call it input stage, and this is we call our gain stage, right? And together these two it will be our op-amp. Now that is our feedback input terminal. This is our main input terminal to apply the signal Vs, and here you apply the feedback network, right? That is here. Oh, that is a mistake. Okay. Need to go to the, oh no, not laser pointer. Eraser. Okay. Renaming. Okay, guys. So that is how it will look like. So this part here. So this part here is the op-amp, these two together, and then this is our feedback network.
Sir, sorry to interrupt you once again, sir. The presentation stopped, sir.
So you haven't shared the screen, sir.
Yes, sir. It stopped for some reason.
When did it stop?
Sir, 30 seconds ago. Not too long.
The screen was shared. No, how come it stopped?
I don't know, sir. It stopped for some reason.
Okay, let me check. Okay, so what is the problem here? Present. No, why it's not presenting? Maybe it got tired, no? So presenting for a long time.
Yes, sir. It's possible. Yes, sir. It's back again. Thank you, sir.
Good. So this the presentation, this what I'm using this pen tablets first time. So this looks like a childlike drawing, right? So I need some time to get used to it, so I'll get better. Okay, so that is how it will be for an op-amp. Inside it will have the main components. One is some kind of circuitry that will take the difference between the two input signals, and then that will be fed to an amplifier that will be amplifying this. Now, what happens here when you add a load here, load resistance RL, right? Now, that RL will have some effect on the output of the amplifier. If you remember the gain of the amplifier, if you are using a common emitter amplifier, right? If it is a common emitter amplifier, our well-known gain expression minus GM-RL, right? GM is the transconductance for the amplifier, and RL is the load resistance. You see that the gain of the amplifier will be affected. Every time you connect a load, it will change, different gain, right? If the RL is low, then you will end up with low gain. So that is the problem. The RL is going to affect the gain of the amplifier. So how to overcome this problem? So we can have a stable gain. So in order to overcome that problem, there is one more modification of this circuit. it's not working. It's not working for some reason. That is working. That is not going away. That is a problem. Guess what we do in order to overcome that problem? We add another stage here, and that is called the voltage buffer. What is a voltage buffer? Can anybody tell me? We discussed this in detail in device 2, if you remember. What is a voltage buffer?
So it keeps the voltage same, the input voltage equals to output.
That is the function. Basically, what it is. Voltage buffer is an amplifier with gain 1, right? It has
Yes, sir.
amplifier with gain 1, so I wrote here 1. I see. An amplifier with gain 1, and this is also amplifier with gain A. It's a high gain. And there are other properties of the voltage buffer, that is to have very high input resistance. Ideal buffer will have infinite input resistance and 0 output resistance. And what's the main function of the voltage buffer? Main function of voltage buffer. Everyone forgot? So main function of the voltage buffer is to transfer the signal from source to the load without any loss of signal. So if this is the input side, this is our source side, the output of the op-amp, this is the source side, and here where we have the RL, that is the load side. And when you put the voltage buffer, it will transfer the signal from output of the amplifier to the load without any loss of signal, right? And the amplifier, since the voltage buffer, ideally it has an infinite input resistance, right? Ideally it should have infinite input resistance. That means the current flow ideally would be 0. So amplifier will feel that it's open circuit at this end, right? It will feel circuit is open because the current is 0. So that means ideally infinite input resistance, you see that gain will not affect it. The amplifier gain will not be affected. It will not see the RA, right? So you have the original, it will retain the actual gain of the amplifier A. It will not be affected by the load resistance because amplifier will not see the RL, it will be isolated, right, from RL by this voltage buffer. So now we have these 3 stages. One is the gain stage, the other is the at the input stage. We have this circuit that will take the difference and amplify the difference, and we have this the gain stage in between, in the middle, and then at the output we have another stage that we call the voltage buffer, That is our output stage. The eraser is not working. That is okay. Some of these are not working. It's interesting. This is working, this is not working. Okay. Okay, let me draw it in a fresh sheet. So that is our op-amp, all this together. And we have our input. And then we have, okay, it's the gain stage. And then we have the output stage. So here we apply our original signal, here comes the feedback signal, right? And you get the output here. The input stage basically is a difference amplifier or a differential amplifier. So that will discuss how to design and construct the difference amplifier. If the input of every op-amp is a difference amplifier, the function of the difference amplifier is to take the difference between the two signals and then supply it to the gain stage. So in the gain stage, mostly we have the common emitter amplifier because common emitter has the highest gain among the three configurations, right? Common base and common collector, common emitter has the highest gain. And we can have a single stage or we can have multi-stage common emitter amplifier to have high gain, enhance the gain. Then at the output stage, we have a voltage buffer. And voltage buffer, there are many different design of the voltage buffer. And with that will, you have a load. So different load resistance will have different requirement of current and voltage. So depending on that, you have to design your voltage buffer accordingly. right? Some voltage buffer, some load will require less current, some will require high current. So depending on the requirement of the load, right, you design your voltage buffer accordingly. And so we have op-amp with different specifications, different current and voltage rating, and different sizes, different power rating. Right? So that's the basic concept, and that is how the concept that came from the feedback theory, feedback amplifier, and that led to the development of the operation amplifier. Guys, any question? So we learned about the different components of the op-amp first, right? What we have inside the op-amp. One is the difference amplifier, the other is the just normal amplifier, the other is the voltage buffer at the output. So the voltage buffer usually also a power amplifier that is designed in a special way that can supply high power to the load. It's also, we call it a power amplifier. And there are different techniques to boost the gain of the amplifier. We can enhance and what is the motivation to achieve very high gain? Motivation was that this product A beta has to be much larger than 1. If this is much larger than 1, then we can write the overall gain is 1 over beta, right? Then it becomes independent of the gain A. So the higher is the gain A, the more accurate will be this expression, right? And more stable your gain will be. The more independent your amplifier will be, independent of the gain of the basic amplifier. So that was the main motivation to make the gain of the amplifier very high, right? So and we say that ideal op-amp has infinite gain, but practical op-amp, the gain ranges from 10 to the 5 to 10 to the 6, hundreds of thousands to about 1 million. So we the op-amp are designed with a very high gain. That was the main purpose, right? To have a very high gain for the op-amp, so that this this is true, right? This condition is true, and the feedback, the overall gain is 1 over beta, independent of the gain of the basic amplifier. Guys, any question? Is it all clear? Are you there, guys?
Yes, sir. No questions, sir.
No question?
Yes.
So I think I'll stop here because time is almost up. We have only 4 or 5 minutes left. And so, let us discuss the insights, the different components of the op-amp. And the course content, let's take a brief look at the course content, just what we have in this course. So basically you see that the amplifier is the main component. The gain stays and the output stays, which is also an amplifier. So voltage the gain, amplifier gain 1. It's also an amplifier. So main focus is on the amplifier, the operation of the transistor as an amplifier in different configurations, the common emitter, common base, common collector. Right? So we'll review those. I have already advised you, recommended you to go through those sections in the Sidra Smith or other textbooks. And Then we have the multi-stage, right? Multi-stage, we have different configuration, one called the cascade configuration, this is called the cascade configuration. And that enhances the gain of the amplifier. The other is the differential pair. It's called the differential, the difference amplifier that we're talking about at the input side. You need to take the difference between the two signals and produce an output that is proportional to the difference. So that is achieved by this circuit, which is known as the differential pair or difference and differential amplifier. It takes the difference between the two inputs, say plus and minus. So VID is the difference between the two signals. So that we will learn about this. Then we have multi-stage differential amplifier. So at the input stage, it can take the difference, and also we can have the amplification of this signal, because overall we need a high gain. So we can also have the boost the signal, and so that led to the multi-stage differential amplifier. Then current sources and current meters. You need to bias the transistors, and to bias the are used. The biasing technique that is used in the integrated circuit is different from the biasing technique that is used in the discrete circuit. In the discrete circuit, you see you have a series of resistors that are used to bias the transistor, but the integrated circuit that is not quite feasible, because you need to make the chip size small, keep the power consumption low. Resistors, they take a lot of space and consume a lot of power. So to avoid that, a different biasing technique is developed for integrated circuit, that's biasing using the current meters. So we learn about these current sources, current meter, how they are constructed, how they are designed. You see that this is the differential amplifier multi-stage that is biased using the current sources. Okay, so these are the cascade amplifier and active load. Okay, we'll say that the differential pair with the RC also works as the load resistance in the amplifier. So this RC resistance again we replace by the transistor that works as the also works as the load resistance. The output, the amplifier transistor has an output resistance R0. So that R0 is basically working as the load resistance here. So we will discuss about the active load, how we use the transistor as the load resistance, and that minimizes the space requirement, and at the same time boosts the gain to a very high value. So this is the amplifier with active load. So that's another concept developed for the integrated circuit, and that is on example how it looks like the power amplifier at the output stage. So a little bit complicated, it looks complicated. Okay. So that is a simple op-amp. That is first op-amp developed in 1964, and that was in 1968. It's a bit advanced. And these are the textbooks that recommend. Okay, so that is the gradual development of humankind. Okay, this one, the previous semester, this is not for this semester. We probably still thinking about it, how we can distribute the marks for the different components here. So that's all for today. And do you have any question, guys?
Sir, will you add the course in Bucks?
Yeah, they will be uploaded. The video lectures will be uploaded in the class.
Alright, sir, is there a specific date when you will add it so we can enroll into the course?
I think Box is not ready yet.
Alright, sir.
Okay,
Thank you, sir.
but hopefully sometime next week.
Okay, sir. Thank you.
Okay, guys, that will be all for today, and I will see you in our next class. That will be next week, right? And till then, stay well and stay safe. And bye from me.
Alright, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
আসসালামু আলাইকুম স্যার।
চলে গেছে ভাই।
স্যার চলে গেছে?
হ্যাঁ।
এই ইয়া ইনি দীপ্ত আছে? এই ওয়াসি কি খবর?
লিস্ট আছে দেখে নাও।
চলে এসে।
রেকর্ডিং কে স্টপ করবে।
ও মাই গড, সরি।